In today's video, we're going to discuss our first reaction of alkyl halides, a substitution reaction known as an SN2 reaction. SN2 gets its name from being a substitution reaction. The N, which is often written as a subscript, stands for nucleophilic, and the 2 means that there are two molecules involved in the rate determining step. So let's break that down a little bit further. A nucleophile gets its name from being a nucleus lover. They often have lone pairs. They're often negatively charged. And this is really just another word for a Lewis base. So we've seen reactions similar to this before. Some characteristics of a nucleophilic reaction are that it's going to have a leaving group. In the case of the reaction shown here, this bromine is going to act as our leaving group. It must have a nucleophile, and in this case, it's going to be our methoxide. So remember that I can redraw this methoxide, or sodium methoxide, as Na plus and O me minus. And so in this case, our nucleophile, O me minus, is going to make a new bond with carbon. And it's a concerted mechanism. That means that it's going to happen in a single step. And so for this reaction, we would see the electrons on that methoxide come in and attack the carbon with the bromine attached. And that's going to give that carbon 5 bonds if I don't break something. And so in the same step, that bromine is going to leave. So leaving groups are called leaving groups because they leave. And we're going to get a new carbon-oxygen bond plus sodium bromide. Often when I'm concerned about the products of a substitution reaction, I would only care about the organic product or the new ether that we formed in this reaction, and I might often leave off the sodium bromide as a major product. If we look at the reaction coordinate diagram for this reaction, it happens in a single step, and this particular reaction is exothermic. And so my starting materials were this alkyl bromide plus Naomi. My products were a new methyl ether and sodium bromide. And it happened in one step. And so I have one transition state, which remember we abbreviate with this double dagger. This transition state looks like this. We've got a CH3 oxygen forming a bond with carbon. Remember, there are two hydrogens attached to that propyl bromide. And then this was the CH2, CH3 dangling off. And the Br bond is breaking at the same time as the CH3O bond is forming. And so there's going to be a slight partial negative charge on that oxygen and a slight partial negative charge on that bromine as these bonds form and break. So this happens in a single step, and because this is a single step, this step must be the rate determining step, and the rate of this reaction is equal to some rate constant K times the concentration of the alkyl halide, in this case propyl bromide up here, times the concentration of the nucleophile, in this case methoxide ions here. There are three main factors that affect the rate and sort of quality of an SN2 reaction. The first is the nucleophile, which I've abbreviated NUC with a pair of lone pair on there. And you must have a good nucleophile or a strong nucleophile for an SN2 reaction to occur. For the electrophile, or the substrate is another word for this, it must be sterically available and have a reasonably good leaving group, or this X. And the solvent must be polar and aprotic. So let's break down what those things mean, starting with the nucleophile. So a nucleophile, factors that affect nucleophilicity. A strong nucleophile is negatively charged. Rather than neutral. And so this would mean that something like an OH minus is a better nucleophile than water. Both of those could act as nucleophiles. They both have lone pairs. They both can donate those in a Lewis-based fashion. But OH minus is negatively charged, and so it's going to be a better nucleophile. The second factor is they involve less electronegative atoms. And so this would mean that, again, OH minus is going to be a better nucleophile than something like F minus. Remember, F minus is highly electronegative. It's greedy, so it doesn't give up electrons easily. The third factor is that they are large and polarizable. I like to sometimes describe this as fluffy. And so that means that I minus is better than Br minus, which is better than Cl minus, which is better than F minus. These large atoms can start to form bonds further away. And so that's going to make them better nucleophiles. I'll give myself a little more space. The fourth thing that affects a nucleophile is that they're not bulky. And what we mean by that is something like a methoxide, OMe minus, is way, way better than something like an isopropyl alkoxide, which is way, way, way better than tert butoxide, which I would say is not a nucleophile at all. It's just a base. If we consider the transition state of this reaction, of the SN2 reaction, the bulky base or bulky nucleophile not working makes perfect sense. So if we look at the transition state, in this transition state, we have a leaving group leaving like a bromide, and a nucleophile coming in. And if this is just a methyl group attached, it's not very big. We've got some hydrogens hanging off of that carbon there. But if this is a tert butoxide, this is a CH3 there. We've got another CH3 hanging out down here. And one more hanging out back there. This is just a bulky group, and so there's a lot of steric clash happening there, and so big nucleophiles are not good at SN2 reactions. The second main factor that affects SN2 reactions is the nature of the electrophile. And I'm going to split that into two categories. The first is the nature of the leaving group X. And so you need to have a good leaving group. Electronegative atoms make good leaving groups. That's because the more polar CX bond is more reactive. They must be stable once they leave. So Cl minus, Br minus, and I minus are all good leaving groups because they're stable once they leave. They're the conjugate base, which I'm going to put in quotation marks, of strong acids. So they're highly stable once they leave. OH minus is a bad leaving group because it's a strong base. It is not stable. And much like nucleophiles, they're also large and polarizable. Which means that I minus is excellent. F minus is lousy. The second part of the electrophile affecting rate of SN2 reactions is its steric bulk. For much the same reason that the nucleophile shouldn't be sterically bulky, the electrophile should also not be sterically bulky. So if we look at a few different types of substrates, the methyl substrate, so something like a methyl bromide. Has a relative rate of about 1,000. A primary substrate, something like ethyl bromide, has a relative rate of about 50, so substantially slower than methyl, but still pretty fast. A secondary bromide like isopropyl bromide, or another name for that is 2-bromopropane, has a relative rate of 1, so we've slowed down substantially at this point. And a tertiary bromide, something like T-butyl bromide, has a relative rate of less than 0.001. And so tertiary bromides don't do SN2 reactions. Methyl primary and secondary do have access to substitution or SN2 reactions, with methyl being the fastest. Secondary is pretty slow, but can happen. And so again, if we look at the transition state of this reaction, if we think about a tertiary bromide, that should show that bond to bromine as breaking for the transition state. There's just not enough room in here for a nucleophile to come in and attack. And so this transition state is very high energy and doesn't form when we're looking at a tertiary bromide. The last main factor that affects SN2 reactions is the nature of the solvent the reaction takes place in. And so there's two different categories we need to consider. The first is polar versus nonpolar, and the second is protic versus aprotic. And this just means it's got whether or not it's got an acidic proton. So protic solvents have acidic protons. Another way that we think about that is, do they have an OH proton or an NH proton? Solvents with OHs or NHs are deemed protic. Solvents that do not have an OH or an NH in them are aprotic. So protic solvents decrease the nucleophilicity, and so they slow down lots of SN2 reactions. If we look at something like F-, a protic solvent such as, say, methanol will hydrogen bond to the F- and sort of trap it so that this F- is protected and it can't do nucleophilic attack. And so protic solvents are not good for SN2 reactions. If we consider nonpolar solvents, nonpolar aprotic solvents, these increase nucleophilicity of nucleophiles, but they have poor solubility of nucleophiles and substrates and the substrates involved. And so things like benzene or hexane would increase the nucleophilicity of nucleophiles, but the substrates wouldn't be soluble in those solvents, and so they're not great solvents for SN2 reactions. That leaves polar aprotic solvents as ideal for SN2 reactions. These include things like THF. This is THF, or tetrahydrofuran, acetonitrile, which looks like that. Sometimes it's abbreviated MCN or acetonitrile. DMF, or dimethylformamide. Looks like this. This is DMF, which is dimethylformamide. And acetone. These are all great solvents for SN2 reactions because they're polar. If you look, I can see THF is polarized that way. Acetonitrile is polarized this way. DMF is polarized this way. And acetone is polarized this way. They're all very polar solvents, and so substrates are soluble in them, but they are aprotic. There are no NH or OH bonds that are going to hydrogen bond to the nucleophile and decrease nucleophilicity. The last aspect of SN2 reactions that we need to talk about is the stereochemistry of SN2 reactions. And these occur with what's called inversion of configuration. What that means, if we look at this particular reaction with sodium iodide and 2-chlorobutane, if that chlorine is on a heavy wedge and the product, my iodine, is going to be on a hashed wedge, or it's going to be going into the page instead of coming out of the page. Remember that this mechanism involved iodine attacking the carbon with chlorine and then that chlorine leaving. This iodine must come from the backside. So if we look at the transition state, this chlorine, or this alkyl chloride, we can redraw with the Cl there. That hydrogen is going to be going back into the page there. This methyl group is going down, and the ethyl group is going up. The iodine has to come from this side. And so if we look at that transition state, going to the product, we get this, which if we do a little rotation is the same as that product. And so SN2 reactions occur with complete inversion of configuration. If this CL is on a heavy wedge, the I is going to be on a dashed wedge. And if that CL was on a dashed wedge, this I would have been on a heavy wedge. That's going to wrap up today's video. We'll pick up with some practice problems on this next time we meet in class.